So my name is Rebecca Frei, and I am a PhD student supervised by David Olafelt in the Department of Renewable Resources and the Faculty of Agriculture, Life, and Environmental Sciences. And first off, I'd like to thank the CSA for organizing this conference and bringing us all together. I've learned a lot from all of you, and I look forward to learning even more today. And my presentation focuses on peatland disturbance and the effect on water quality. And to begin, I'd like to add my acknowledgement that my office and field site are situated on Treaty 6 territory, the traditional lands of First Nations and Métis people. So as I said previously, I study water quality in streams. And as we're all well aware, water is essential to life, and the quality of water is intrinsically linked with the land. And throughout the world, and especially in the north, we are facing widespread water quality issues, including water brownification, which is primarily caused by an overabundance of carbon in the water, and eutrophication and harmful algal blooms, which are primarily caused by the overabundance of nitrogen and phosphorus. And the consequences of these issues include untreatable water or prohibitively expensive water treatability costs, fish kill, and ecosystem shifts. So within that context, I'm really interested in how peatland disturbances affect water quality. And peatland disturbances are increasing rapidly due to indirect and direct anthropogenic activities such as permafrost thaw, wildfire, and resource extraction and development. And the peatland disturbance that I will be focusing on in this talk is peat extraction. And as I'm sure most of you are well aware, peatlands are the dominant wetland type in the north, and they're incredibly important for climate resilience because they store massive amounts of carbon and they also store nitrogen and phosphorus as well. So peatlands naturally contribute dissolved organic matter and nutrients to inland waters. Dissolved organic matter is a diverse group of organic compounds that originate from dead organic material, and they contain carbon, nitrogen, and phosphorus, as well as other elements. And because of the natural vegetation and microtopography, the high water table with minimal hydrological fluctuations, that leads to long-term storage of peat organic matter in wet, cool, acidic conditions. And then what we see in streams draining pristine peatlands is high concentrations of carbon, because there's a lot of carbon there present, and then low concentrations of nitrogen and phosphorus, because these systems are very efficient in cycling those compounds. And so the crux of this presentation is how does peatland disturbance affect water quality, especially when thinking about carbon, nitrogen, and phosphorus. So there's a lot of reason to believe that disturbance will affect export of carbon, nitrogen, and phosphorus because often disturbance affects the productivity and hydrology of the peatland. So for example, often vegetation is partially or completely removed. The water table can experience major fluctuations through drainage or flooding, and this all changes the physicochemical properties of the peatland, which could lead to oxidation of deep peat organic matter. So will that result in more carbon, nitrogen, and phosphorus? That's the question. And to answer that question, I have analyzed the stream network of two watersheds in central Alberta, about 100 kilometers west of Edmonton. And we selected these watersheds because they drain large peat extraction complexes, which are shown in brown on this map here. They also include pristine peatlands shown in pink, forests shown in green, and agricultural lands shown in yellow to compare the effect of land use on water quality. We measured 55 sample sites in total, the two watershed outlets, and 53 nested subwatersheds with 27 subwatersheds in the Tomahawk Creek catchment that lies to the east, and then 26 subwatersheds in the Deep Creek watershed that lies to the west. And so just to note that these two watersheds are medium-sized, small to medium-sized, so 188 square kilometers for Tomahawk Creek and 132 square kilometers for Deep Creek. And so the sites that we're measuring, as you can see in these pictures here on the left, range in size from small drainage ditches in a peat extraction complex to small streams coming out of culverts near roadways to larger streams getting close to a river size. And these watersheds, they drain into the North Saskatchewan River. And so we went out and collected samples from these 55 sites 4 times. We were really fortunate to be able to get out last summer. because we were in central Alberta. And so we would go out and measure these watersheds in a short time frame within 2 to 3 days to minimize variability in environmental conditions such as precipitation and temperature. And so we were able to do 4 of those samplings, and we were able to capture high to low stream flow conditions, as you can see from this hydrograph of Tomahawk Creek. So you have water level on the y-axis and then time on the x-axis, and those little yellow dots show when we were out. And that corresponds with these pictures on the right when we were out June through September. So you can see that we were out for a fairly high flow in those June and July months, and then August and September we captured base flow conditions. So what does the data say about peatland disturbance and water quality? Here we have the mean composition of nitrogen and phosphorus for each subwatershed. And so those subwatersheds are ordered along the x-axis from highest degree of disturbance to least degree of disturbance. And as you can see for nitrogen on that top panel, dissolved organic nitrogen shown in green dominates, though ammonium, which is shown in orange, becomes significant and important in those highly disturbed watersheds. And then for phosphorus, phosphate is the main form shown in orange, and phosphorus shows little association with peat disturbance. So there's a bit of a peak with the most disturbed, but then not really an association as you move through with higher peaks with least disturbed watersheds. And when we look at carbon, nitrogen, and phosphorus together, as I show here in these box plots, it becomes more clear that carbon and nitrogen are influenced by disturbance. So on the x-axis, I went ahead and grouped all of the subwatersheds by dominant land cover type. And so on the x-axis, you have disturbed peatlands, pristine peatlands, agriculture, forest, and then mixed. And that mixed represents the larger subwatersheds and the main watershed outlets that they cover a very heterogeneous landscape. So it's hard to say, to classify into one or the other of those landscape types. But here we see that the disturbed peatlands do have elevated dissolved organic carbon on that top panel and ammonium as well in that middle panel in relation to other land cover types. And like in the phosphorus bar plot on that bottom panel, we see no difference between disturbed peatlands and other land covers. And so to summarize, we have these little pictures on the right with those little water drops. So essentially disturbed peatlands have elevated carbon and nitrogen, but equivalent phosphorus to other land cover types like agriculture, where we see lower carbon, nitrogen, and phosphorus, which is a bit surprising with agriculture that nitrogen is lower than these disturbed peatlands. So that was an exciting find as well. But it's important to note that this data is a little bit more nuanced. When considering the effect of disturbed peatlands, we also have to consider them in relation to pristine peatlands. So in these plots here, we have the percentage of wetlands, pristine wetlands and disturbed wetlands, just wetlands generally, plotted against dissolved organic matter characteristics. So on the top panel is dissolved organic carbon concentrations, and on the bottom is SUVA, which is a proxy for organic matter quality. And so drawing your attention to this top plot with DOC versus percent wetland, those dots are colored by the amount of disturbance in those subwatersheds. And as you can see, there's a pretty good linear relationship between dissolved organic carbon and the percent wetlands in the watersheds, which is consistent with other studies that wetlands have a lot of carbon and they enter the waterways. And so even though those disturbed sites, those highly disturbed sites are on the top end, it could be that if those watersheds weren't disturbed, they would give off the same amount of carbon anyways, just because they're wetlands. And so that shows a little bit of sampling bias in our study. And so we can't definitively say that the dissolved organic carbon is because of disturbance. That high amount of dissolved organic carbon is because of disturbance. And we see a similar, well, kind of a similar trend with SUVA, that there's not really a relationship between, or a difference between the disturbed and undisturbed sites with organic matter quality. And so to summarize those findings in these pictures, disturbed peatlands and pristine peatlands have similar organic matter concentration going on. And so when we look at the nitrogen, this story is consistent. It appears that the disturbed peatlands do have a major influence on ammonium concentrations beyond what would be expected if the peat were not disturbed. And so to summarize with those pictures, ammonium is higher in disturbed peatlands above what would be expected if they were pristine. Which begs the question, will these disturbed peatlands lead to further browning and eutrophication of downstream waterways? And I believe the short answer is no. Here I show subcatchment leverage, which is an indicator of the influence each subwatershed has on the watershed outlet concentration. And if the subwatersheds have an average positive leverage, as shown by the orange diamonds, then that indicates net retention or removal within the watershed. In other words, rapid processing of that nitrogen, as can be seen for dissolved inorganic nitrogen and phosphate. So nitrogen and phosphorus do have means below the line, and so that, or below that zero line, and so that leads or indicates rapid processing. And then for dissolved organic carbon, we see mean values close to zero, which indicates a neutral mass balance. In other words, inputs equal outputs. Therefore, little of the dissolved organic carbon is processed within the catchments or watersheds before it is exported to downstream ecosystems. But the inorganic nitrogen and phosphorus are quickly processed and taken up before export. And so what all this means in conclusion is that disturbed peatlands may increase the amount of carbon and nitrogen entering waterways, but they have less of an influence on phosphorus. But we were not able to definitively say that carbon is elevated because of the disturbance, because wetlands naturally contribute carbon to waterways. And finally, as we saw from the leverage analysis, in this scenario, it seems likely that the watersheds are resilient to these disturbances and are able to handle the influx of nutrients by processing and removing them within the stream network. And though this is good news, I do believe we need to be cautious about how we manage our peatlands for both the sake of the climate and for water quality. And so with that, I would like to say thank you to my funding sources and to my lab mates and research partners for helping with this project. Thanks.